Hello everyone, welcome to How Go Scheduler Works Part 1. This, is this video is split up in 3 parts. This is part 1. My name is Rajan. I'm an experienced backend developer with 10 years of experience into backend development. I work in Golang, PHP, Laravel, CodeIgniter, and various other technologies. I've been developing REST APIs, gRPC, socket-based applications, queue integrated solutions, cloud integrated solutions, containerized, non-containerized deployments using Docker and Kubernetes. Other than this, I've been working in parallel computing as well. My various projects involved parallel processing, multi-threading, multiprocessing. I've also worked on data processing, data analysis, and data visualization, and has experience developing applications with real-time data processing and data streaming. Additionally, I have also worked on tech stack migration projects, service mesh integration, on-premise solution, and on-premises to cloud migrations, implementing these across both microservices and monolithic architectures with distributed and hybrid systems. Let's understand what is a GoRoutine. In layman terms, GoRoutine is just another method which can be launched in parallel to the main execution thread and has the ability to run in parallel while rest of the code can execute independent of its execution. Main points of GoRoutine should be low memory consumption. Since GoRoutine runs in the same address space, shared memory can be accessed across multiple GoRoutines, and data or instructions can be shared across executing GoRoutines through Golang channels. Golang achieves concurrency and parallelism through GoRoutine. How GoRoutine is managed and why it's different and stands apart from OS threads available in other languages. Let's try to understand underlying technology which makes it different. What is a Go scheduler? The Go scheduler is a component of the Go runtime that handles the execution of Go routines. It operates as an M-to-N scheduler, which means it multiplexes M Go routines across N operating system threads. The main responsibility of the Go scheduler is to efficiently distribute Go routines across the available threads in CPU cores. To understand how it works, we have to understand cooperative multitasking and preemptive multitasking. In this video, we'll be talking about cooperative multitasking, and then we'll be able to explain how this is related to Go scheduler, what are Go routines technically, and how and why Go routines are considered a lightweight component. Let's understand what is an application. An application is nothing but a set of instructions. These set of instructions are expected to be run in a sequential manner or in a certain order of fashion so that these instructions can be executed properly. Who executes these instructions at last? Processor is the one who executes these instructions. For the sake of simplicity, we'll be considering one processor, one core, and one thread at a time, so that we are not involved in a lot of complexity. We'll get to that, but we'll start with this. Most important, these instructions needs to be executed in same order in which these are programmed by a developer. How it is made possible? Operating system acts as a mediator between your set of instructions and processor. There is a CPU and processor, so our instruction from our application don't reach to CPU or processor directly. OS acts as a mediator between our application and processor, which transfer the control of threads to the CPU. I'm not going to detail how it is done. We'll be focusing more on the technical implementation and the cooperative multitasking here. Operation system traces instructions so that they can be executed in predefined order. Let's suppose there are 10 number of instructions here. So when any application executes, it is expected that these 10 instructions are getting executed by the processor in the same manner that it is expected to be. So operating system takes care of this thing. So how does an operating system take care of this? Operating system creates an application thread. Let's consider T1 here. So When any application comes for an execution, OS creates one particular thread and assigns it to that particular application. This particular thread is responsible for executing this application and the set of instructions that it holds in the same manner that it is expected to be. And also, using this thread, operating system can trace execution of instruction and their order. This should be the flow of communication. Thread acts as an input to the processor. So, using a thread, processor gets to know which instructions to execute and start the execution. This is one of the reasons we call it a thread. We connect the instructions to the processor in the order of execution. This is what basic application executions look like. Now, let's assume there are two applications, and application 2 also has a set of instructions and a sequence in which they should be executed, and you want to execute second application as well. And it is a very common scenario when when a person is using a laptop, for a developer a text editor is there, a browser is there, and many other applications can be there. So this is a very normal scenario. Operating system cannot mix up executing instructions of both application, and hence these application 1 and application 2 should be executed in a certain manner, and instructions for application 2 should be executed in a certain order. How OS ensures execution of application 1 and application 2 independently without mixing their instruction or order of instruction. So order creates one more thread, T2, just the way it created for application 1, and this application 2 is connected to thread 2, and then this communication goes to CPU and the processor. Now we have two different applications waiting to execute via two different threads, T1 and T2, in the same processor. How processor decides what is to be executed? Can a processor execute more than one instruction at any point of time? No. One processor can execute only one instruction, and it can be either from application 1 or application 2 at any point of time. So how a decision is made to execute instruction 1 from application 1 at T1, let's say timestamp T1, and T2 execute from application 2. There are several strategies followed. In pre-Windows operating system 3.1, in early 90s, in early operating system, a strategy known as cooperative multitasking is used. What is cooperative multitasking? Application will decide when they don't want the processor time. What is it? Let's try to understand this. Let's say application 1 performs IO operation at T1. When you're performing IO operation, application 1 don't need CPU time. So what is expected is, whenever any application reaches a state where it is not going to use the processor time anymore, application is expected to deprioritize the processor time to operating system, saying, boss, that I'm going to wait for some time to get data from database queue or whatever the source, and till that time application 1 don't need processor time, and allow processor time for some any other application who needs processor time at the moment. Operating system will allocate the processor time to any other waiting thread, let's say T2, and processor will execute the instruction from application 2 traced to T2. And let's say after some time, thread 2, which T2 is executing IO operation and don't need processor time. Same process of relegation happens, and OS allocates processor time to, let's say, application 1, assuming there are only two applications running at the moment. These applications have to coordinate among themselves to allocate the processor time appropriately and effectively. If there are more than two applications, different strategies can be used to allocate processor time to different applications, but the decision if processor time is required or not is decided by the respective application. This was in the old OS. Subsequently, when more and more applications are executed at the same time, frequency at which the application gets the processor time gets reduced. Let's say if there is only one application, it can utilize 100% of processor time. If there are two applications running simultaneously, it reduces to 50%. And in an event there are multiple applications, processor time allocated to every application reduces drastically. So, to keep processor time to itself, since processor time availability is crucial, application developers started hang on to processor time to ensure processor availability even when the processor time is not actually required. Same tricks were used by developers to hang on to processor time as availability of processor time was crucial but uncertain as gap between processor time allocation increased. Until then, the waiting application cannot do anything and become unresponsive to the user. Imagine there are two applications. One application is just waiting for some is performing some IO operation and has nothing to do with CPU time. But to avoid passing processing time or processor time to the other application, it just keeps hang on to the processor and doesn't pass control to the other application to execute. So what happens is application one or any one of the application who's hanging on to the operating system or the processor time keeps runs smoothly while the other goes into a hang mode. Here, cooperative multitasking strategy fail. Obviously, operating system designers have to find a solution to the problem as executing multiple applications become crucial. And nowadays, at a time, almost 10 to 20 applications have been running even in the mobile phones as well. In this quest, operating system designers realize only when operating system gives control to application to decide whether they need processor time or not, the problem arises. So let's not give the control of to application, and OS should take control over it, and operating system should decide process time is allocated to which application at any point of time. This somehow reduces the dependency of passing the control from one application to the other since OS is taking care of it. Now to do that, operating system introduced thread scheduler. So what happens in thread scheduler is everything remains the same. The fact that operating system deploys a thread scheduler. This thread scheduler is going to decide which thread or instruction from which thread will be executed by the processor at any given point of time. Now the control of executing, which was earlier with the application, is no longer with the application anymore. It is passed to the thread scheduler. And thread scheduler, which resides in the OS operating system layer, decides which application and which instruction has to be executed at a particular point of time. So how this decision is made? Operating system allocates a predefined window to each and every thread. Let's say 10 to 15 milliseconds. When 10 milliseconds of any thread are completed, regardless of the action of execution of the thread 1, it simply pursues the state of thread 1 and somewhere and then allocate the processing time to other thread. Let's say thread T2. In this way, execution of previous executing thread was not lost. So in this way, operating system took control of executing threads, provided a predefined windows to the threads. This strategy is called as preemptive multitasking. It's important to remember both strategies here. Strategy 1, application decides processing time, which is called cooperative multitasking, and strategy 2, where operating system decides processing time through thread scheduler, which is called preemptive multitasking. That's all for this video. I'll continue in the next video by explaining what is preemptive multitasking and how cooperative multitasking and preemptive multitasking are connected to Go Scheduler and how the underlying infrastructure or underlying technology in Golang language affects everything and how does the performance is so good in Golang. Thank you.